Number 77 है by evaluating integral of I square r dt show that when a capacitor is charged by connecting it to a battery through a resistor, the energy dissipated as heat in the resistor equals the energy stored in the capacitor. This is a capacitor charge in circuit. The battery has a voltage V, and when we connect it to a resistor to charge this capacitor, a current will start flowing. And this flow of the current has a graph something like this. Initially there is a high current flowing into it, but it gradually decreases with the temperature. When the voltage V here becomes equal to the voltage on this capacitor, the current through the resistor becomes zero. And then the energy stored in the capacitor, eventually the voltage V will appear on this capacitor, and in that situation the energy stored in the capacitor is given by half CV naught square, where V naught is the voltage on the battery. We need to show that this energy stored in the capacitor is same as the total energy dissipated in the process on this resistor R. Now the power on this resistor P will be given by I square R. The current in this resistor is varying with time. So this power in this dissipated in this resistor will also vary with time, and that power will be given by I square R, where I has a value some I naught e to the power minus t by RC. Now the energy dissipated as heat in this resistor will be given by, in a small amount delta T, will be given by this power multiplied by dt, or if we call it dt, then du is equal to I square dt. In the problem they have already shown it that we need to integrate it, but we just wanted to make sure that we understand what that means. So the energy in this time from, let's say, t equal to 0 to t equal to infinity can be found by integrating this whole term over the period of time. So du is I square r dt, and r is constant, so it comes out, and I square is given by I naught e to the power minus t by RC. So this whole thing becomes 0 to infinity I naught square e to the power minus 2t by RC, because this whole thing, this is the expression for I, which varies with time. By squaring it, it becomes I naught square e to the power minus 2t by RC. Now instead of I naught we can write V by R, because I naught is the initial surge current. Initially the voltage on here is V, on this point we can assume to be 0, so the initial surge current is V by R. So this I naught is V naught square by R square, the square of this R and this R cancels, so because V naught square by R, integral of e to the power minus 2t RC dt. Integration of this thing is integral of this term, integral of e to the power x dx is e to the power x divided by differentiation of this, which is minus 2 by RC. Now this R cancels, we have 2 by C becomes C by 2, so it's V naught square C by 2, and in this term if we write E infinity in terms of t, if we write infinity, it's 1 upon e to the power infinity, which is 0, and there's a minus sign here, so this is plus here, this becomes here, and then when t equal to 0, this is e to the power 0, which is 1, that becomes here. So this energy dissipated as heat becomes this one, and this is equal to the energy eventually stored in the capacitor.